Hey everybody, Graham here. So in the comments on my last video, several of you indicated that you'd be up for a physics video. So here it is. I'm gonna try to keep it reasonably brief because I tried to record this once before and the video got super long. So I'm going to try and keep it relatively short. And what I'm going to talk about is mainly the central problem in physics and sort of my interest in it. So I'm assuming in this that the people watching don't really know any of this stuff, or maybe they know a little bit of it. If you are a physics enthusiast or a physics head, you're probably going to be able to find stuff in here that you can pick apart. This is a very broad thing, and it's not very technical. So I got interested in physics back when I was a kid. In school, my high school physics class, we took a trip to the university in my state, and we got to watch some of the interesting physics thing. We got to look at, sort of like the graphics that come out of the bubble tanks and stuff like that. And it was very, very interesting, and I really loved it. And I had the idea that I would like to be a physicist, but I've always known that I don't have the math skills for it. I don't suck at math. I'm actually pretty decent. I got through some fairly advanced stuff in college, but of course that was 35 years ago. Wow, 35 years, Jesus. When I hear a real physicist talking about math, they understand the math in a way that I never did. They can look at an equation and understand what it's describing. Or they can look at a physical situation and have in their head the general form of an equation that would describe it. And I just can't do that. I can calculate, I can follow rules, I can do logic, but I can't make that translation between the math and the physical world the way good physicists can. The whole math thing, so now we're going to get into a little bit of history. The whole math thing kind of sort of started with Newton. Newton invented calculus, as did Gottfried Leibniz. They developed it independently, and there were some pretty good arguments about that, apparently. But at the end of the 17th century, Newton published his book, Mathematical Principles of Natural Philosophy. Of course, it was in Latin, so most people refer to it as the Principia. And the Principia was it for centuries. It seemed as though Newton had figured everything out. He came up with a new kind of math to describe it. He described it. And there was a time where people thought we kind of knew everything there was to know about physics. We know how things move. We know how, we know what happens when things crash into each other and so on and so forth. And this was sort of the understanding of physics for a long, long time. Now, there are two problems with Newton's physics, and we can't really blame Newton for these problems because he had no way of knowing about them. Once our instruments became more precise and we were able to take measurements, we found a few situations where Newton's laws break down. For example, when they used Newton's laws to try to calculate the orbit of Mercury, they would always come up a little bit off. And that was a big problem. Nobody understood why. The why was figured out by Einstein at the beginning of the 20th century. In 1905, he published the theory of special relativity, and 10 years later, in 1915, he published the theory of general relativity. And what relativity says is that the reason that Mercury's orbit is a little off is that it's close to the sun. And in the presence of a large mass or a large amount of energy, which is the same thing, that time was passing more slowly for Mercury than it is for us because it's closer to the sun. And when they used Einstein's laws to calculate the orbit of Mercury, it came out right. And subsequent to that, pretty much every test of relativity has proved to be right. It did make some predictions, such as the prediction that that large masses would bend light, and they do. If you were able to watch a star pass, become eclipsed by a black hole, for a moment you'd see a little ring around the black hole, which is the light of the star going around the black hole. I think. I could be wrong about that. The black hole might be strong enough to suck everything in, but I'm assuming that this happens outside of the event horizon. Einstein's laws have been tested and have generally come up to be pretty good. Now, there are certain places where people are starting to question them a little bit, and that sort of ties in with the central problem. The other problem with Newton's physics is that it broke down at the very, very small levels. So we needed relativity to explain the very big levels, and we needed quantum mechanics to explain the very small levels. And this has also happened around the start of the 20th century, late 19th, late 19th, early 20th century. Guys like Niels Bohr and Werner Heisenberg were studying atoms and the constituent parts of atoms and noticing that they didn't behave the way they expected them to behave. And I could make a very, very long video if I went into all of the ways that quantum mechanics is weird. But what I'll say about quantum mechanics is that you can only ever talk about it in terms of statistics. You can set up an experiment whereby, you're shooting electrons through some kind of apparatus, and there's a place where an electron could go either way. And all you'll ever be able to say is that X percentage of photons went to one place and Y percentage of photons went to another place. But you will not be able to tell which photon took which route. And more than that, if you try to figure it out, you will come up with stuff that seems to indicate that they all took all the routes. A lot of people really don't like this, and I'm one of them. It just seems odd that pieces of matter should be able to behave in this way. But they do. And so they defied Newton's laws. So we have sort of three areas of physics. We have sort of the everyday physics, the sort of human scale physics, which is covered by Newton. We have the physics of the very large, very heavy, very energetic, which is Einstein. And we have the physics of the very small, which is quantum mechanics. Now, the problem is relativity and quantum mechanics don't work together. The math is such that if you try to solve one with information from the other, you will get something that doesn't make any sense. Such as you might try to figure out the mass of a particle and you'll come up with a mass of infinity, which, is clearly nonsensical. You can't have an electron that weighs infinity. The mass of an electron is very, very tiny. Now, to some extent, this doesn't really matter because quantum mechanics works really good for the small stuff and relativity works really good for the big stuff. So why do we need something that allows both of these things to exist at the same time? Well, there are a couple of reasons. The first reason, I think, is mainly, I want to say aesthetic, but it's more than that. It's more of an intellectual thing. It's like there's one universe, at least that we live in, and we should be able to understand how that universe works at all scales without having to change our mode of analysis, right? I mean, physics works the same way for my car as it does for a guitar pick. So there's no reason that physics shouldn't work the same way for a star that it does with an electron. It's just that we don't have a theory that addresses the entire continuum. And a lot of people, like myself, think that we should. Now, it's possible that it doesn't exist, but I don't really believe that because the universe is the universe. It's not subdivided into little, subdomains. So anyway, I'm not the only one who feels this way, and so a lot of people have been working for a long time to solve the problem of unification of these ideas. And it generally goes under the heading of quantum gravity, right? Because relativity is, to a substantial degree, a theory of gravity, and we're looking for what the effects of gravity are on a very, very small scale. There are only a couple of times where the quantum and the relativistic would interact. Some of these things are in terms of speed. For example, photons do not experience time because they travel at the speed of light. But also, in, say, the inside of a black hole, you have something where a lot of matter is compressed down to a very tiny, perhaps quantum point, but the gravitational effects are huge. So that's a place where we could use something that integrates both theories. Another one, and this one's probably more important for actual research, is the very early universe, right around the time of the Big Bang. Assuming that the Big Bang actually happened. There are some questions about that as well. But if the Big Bang theory is correct, there was a period where the universe was compressed down into a very small point. And there again, you would expect to have quantum mechanical effects and relativistic effects going on at the same time. So the fact that we don't have a theory that ties both of these things together is a problem for a lot of people, not for everyone. There are people who are just sort of like, these theories work over here, these theories work over there, everything's good. But that is deeply unsatisfying. So for the last 40-ish years, I guess, the main contender for something that would explain all of this stuff has been string theory. String theory says that instead of little particles like little electrons or neutrons or stuff, you have little tiny strings. And these little tiny strings vibrate, and how they vibrate determines what kind of particle they are. There was some early success with string theory. String theory has some really interesting features. The problem with string theory is that it doesn't do a whole lot in the way of making testable predictions. because these strings are at such a tiny length on such a tiny scale that we will never be able to see them, no matter how good our instruments get. It is not possible to probe that scale because anything you probe it with is going to be bigger, or, assuming some sort of miraculous technology, the same size. And so you won't be able to learn any meaningful information from that. But it does have some interesting mathematical properties, the big one of which is that it predicts the existence of gravitons. Gravitons would be the force-carrying particle for the gravitational force, in the same way that photons are the force-carrying particle for the electromagnetic force, and so on. Now, no one's really sure if gravitons should exist or not. Einstein described gravity as the curvature of space, or the curvature of space-time, more accurately. So when you have a heavy mass like a star or a planet, it warps space, and then things that orbit it are sort of falling towards it. And in that formulation, there's no need for a particle. Space is what provides the force. It's not obvious in the case of other forces like the electromagnetic force or the strong and weak nuclear forces, though all of those forces seem to have particles associated with them. And so the question is gravity a completely different thing, or is gravity another force and our understanding of forces in general is not right? Anyway, string theory predicting gravitons was very tantalizing because it would presumably sort of show how we could get to incorporating gravity in quantum mechanics. The problem with string theory is that it doesn't make a whole lot in terms of testable predictions. And for that reason, people can do a lot of math, but until we can test it against something, we don't know if the math is reflective of anything physical or if it's just pretty math. So there are other approaches to quantum gravity. The main sort of challengers is a theory called loop quantum gravity, which basically says that space as we understand it doesn't really exist. That space is purely relational. It is only the separation of objects. And that there is a smallest degree of separation, which is the Planck length. The Planck length is also what they thought about how big they thought the strings in string theory are. Anyway, I find that interesting for the reason that that problem is so deep and so troubling. And the weirdness of quantum mechanics is troubling. And it would be really, really nice if we had an explanation for why quantum objects behave the way they do. I was watching a lecture by Richard Feynman, and this was probably sometime in the 60s that he gave this lecture, so, a lot of this stuff hadn't been discovered yet. And he was talking about the weirdness of quantum mechanics, and he says something along the lines of, he was a very sort of pragmatic guy, and he said something along the lines of, this is how it works. We understand how to calculate it, but we don't know why it works this way. You may not like the fact that we don't understand why it works this way. I don't like the fact that that it works this way. Tough. That's the way it works. So he was a very much, just sort of stop philosophizing and do the math kind of guy. But there are other people who have posited a lot of different possible explanations for this. And so we have string theory, we have loop quantum gravity, and then we have sort of more exotic stuff, like we have the many worlds interpretation, which says that, when you're setting up your quantum experiment and all you can determine is the statistics, that what's actually happening is that every particle takes every path, and every result is different. And every time this happens, a new universe is created. And people find this interesting, and people find this appealing because, number one, it's got that sort of science fiction-y cool thing about it. And I think people just like the idea that there might be parallel universes. There might be a parallel universe where everything is exactly the same, except I'm a billionaire. I'd like to live in that universe. The problem is that people take these speculative ideas and talk about them as if they're fact. And so now if you talk to people, if they're at all familiar with any of this, they'll talk about things like the multiverse, which would be the set of all universes that are created by these splittings of the universe. And that's even in pop culture. I mean, we had that in, if you saw the Doctor Strange movies, there's all this stuff about the multiverse, and people are treating it like it's a fact. It's not a fact. It's a speculation. The math does not rule it out. So it could work that way, but we have no idea whether it actually does or not. And so it does get frustrating to hear people talking about that kind of stuff when you know what's sort of really going on. Now, like I said at the beginning of this video, I don't really grok the math involved. So my understanding of this is very, very, very rudimentary and very, very, very incomplete, because understanding the math is the key to understanding the physics. I mean, you could say that there is only the math if you wanted to. So some of what I've said here may be wrong, and I'm going just by memory. So there's that too. But that is the central question that's in physics right now, and has been for a long time. People have been cranking away and cranking away and cranking away at this problem, and there are things that are promising. Nothing has really been put out where people are looking at it and going, oh, yeah, this is definitely on the right track. String theory was that way for a little while in the 90s, but I think a lot of physicists are starting to think of it as a dead end. Not everyone. I mean, there's still plenty of research going on in string theory. But I think there are a fair number of physicists who have been beating their head against that particular wall for so long that they're just kind of looking for something else. Anyway, so for those of you who were sort of interested in my take on physics, that's pretty much it. That's why I'm interested in it. That's the area of it that I'm interested in. And I can't tell you why I'm interested other than just sheer curiosity, but there you go. Anyway, couple of personal notes. I'm feeling a little better mood-wise. I'm kind of stressed out right now, but overall things have been a little bit better for the past couple of weeks. We got an offer on our condo, so we're just kind of waiting for the buyer to lock down the financing, and at that point we'll set a closing date and it'll be a done deal, more or less. So there's that, which is a good thing. I'm very happy about that. But it also means that we have the daunting task of finding another house. So that's about it. I'll talk to you guys in the next one. I hope you're all doing great. See you soon. Graham out. Bye.